All right, I hear the recording in progress. Okay, so we're here, finishing up 2-3. I will start some of 2-4. And tomorrow you get your next quiz. I'll have it just on the video here. So those of you who aren't joining synchronously, you'll get a little bit later. But even if it shows up later this afternoon at the latest, you have until 11:59 p.m. tomorrow evening to submit the quiz. So there's plenty of time to submit the quiz. That should not really be an issue, I think. Okay. All right, so we're finishing up 2.3 and then start some of 2.4. Okay, again, just like the other quizzes that we had before, you know the way it works by now. It's open book, open notes, open everything. You can help each other out. You can look in the book, consult other people for quizzes. And again, we're already having our next test on the 17th. Okay, you might say, well, it seems like we just had a test. You're right, we're having another one. But on the other hand, that means we don't cover that much material, right? So just this. Again, you have your homework requirement. You must submit at least 70% of the homework. Again, that's to me is kind of a joke because I do such a great percentage of the homework already anyway. In which case, for your putting the homework down, you just have to copy what we did in class and then just go ahead and do, the rest of them. So hopefully that's not too bad. All right, so I'm going to finish up 2-3 and get started on a little bit of 2-4. Okay, so we're going to do the reciprocal functions now. So I think I was done with most of that. Okay, now we're going to talk about the graphs of reciprocals. So I alluded to this last time, the graph of the reciprocal of a function, page 98. All right, so if you have a function which is the reciprocal of a given function, the value of f of x is undefined when g of x is 0. Okay, so that makes sense. Okay, 0 has no reciprocal. So for your original graph, wherever there's a 0, you get an undefined value. So if you take a look at this graph, the blue graph, x-intercept, x-intercept. So for the reciprocal graph, which is the red, undefined, right? The values of f of x and g of x are the same when g of x is 1 or -1. Why? The reciprocal of 1 is 1. The reciprocal of -1 is -1. So here y equals 1, right? The two graphs touch. The two graphs touch. How come? Because the reciprocal of 1 is 1. And the two graphs touch there and there because the reciprocal of -1 is -1. Okay. For each x in the domain of f of x and g of x have the same sign. So wherever f is positive, the reciprocal is also positive. Wherever f is negative, the reciprocal is also negative. So if you look right here, both the red and the blue graphs are positive. Both positive, both negative, both positive. So it's not possible for a graph to be up here, let's say, and the reciprocal to be down there. No, the reciprocal is of the same sign. Okay? So let me just throw out some reciprocals. The reciprocal of 2/3 is 3/2. The reciprocal of 7 is 1/7. Same sign, both positive. And what's the reciprocal of -2? -1/2. Or what's the reciprocal of -4/7? -7/4. So they're either both going to be positive or both negative. So whatever the graph of the reciprocal looks like, it's going to be positive if the original was positive and negative if the original was negative. So notice in this case, the red and the blue graph are always either both positive or they're both negative. And the magnitude of f of x is large when the magnitude of g of x is small and vice versa. Okay, so the bigger one number is, the smaller the other is. So what's the reciprocal of 1 million, big number, 1/1,000,000, small number, right? Likewise, what's the reciprocal of -1 million, negative small number? Well, -1 million, which is a big negative, right? So when one goes up, the other goes down. So see how the blue goes up the red goes down. The blue goes down, the red goes up. Blue goes down, red goes up. Blue goes down, red goes up. Blue goes up, red goes down, and so on.
Can I ask a question about this example right here? So the vertex is 0. Wait, is the vertex is 0, 0, right?
Well, we don't use the word vertex in this case. It doesn't really
Okay.
apply.
Yeah. So would you find like the between like the two middle parts, would you find that reciprocal value using the 1 equals, or would you use the same system as finding the reciprocal of the vertex?
Yeah, okay. If you have the ones, like 1 and -1, definitely. Okay. But I think I know what you mean, that in the so-called vertex, which is not really what it's called, but I guess we'll say maximum and minimum. So the maximum of one becomes the minimum of the other. If that's what you mean, which kind of makes sense, because if this goes up, the other goes down. So where this is a high point, this is a low point. If you and likewise here.
So you would find it as if you were finding a vertex. Oh,
sorry?
You froze up on me.
Yeah. Again, we don't.
Oh,
really
I'm
use
sorry,
the
you
word
froze
vertex.
up on me.
Vertex only
Yeah,
applies
but you
to
would use the
parabolas.
same system. You would use the same system to find that point, though. Yeah.
If you're talking about the negative b over 2a formula, that doesn't work. That only works for parabolas. Okay, so the only way we can find the high or low points is by techniques of calculus, which you'll learn next year when you get to calculus. Then you can
Okay,
find
so
out
we won't be working with lines like this complicated for inverses, for reciprocals.
For reciprocals, no, you won't be looking for maximum and minimum values right now.
Okay,
that's what you mean. Yeah, you can wait. We'll have to wait for calculus for that. So yeah. Okay. All right. So let me do some of these reciprocal functions that we have here. All right. So given the graph, how do you do the reciprocal? So number 11, g of x equals absolute value of x. Okay. Now you should already be somewhat familiar with the absolute value function. It's V-shaped. Okay. But if you don't remember it, you can put it on your formula sheet. Again, I guess one advantage of being under COVID, I suppose now, is if we were meeting face to face, I'd make you memorize it. But now I'm not making you memorize it, but it's V-shaped. Okay, so the original function I have here, the V-shape, how do I get that red one? Okay, so whenever the y value is 1, the reciprocal stays the same. Okay, so I have the point -1, 1, and 1, 1. For the reciprocal function, that stays the same. -1, 1, 1, 1. Second rule, the reciprocal of 0 is undefined, we say. Right? There's no such thing as 1 over 0. Okay, so right here, the bullet that says the value of f of x is undefined when g of x is equal to 0. Okay. So right here, the original function touches the x-axis. So it's undefined for the reciprocal function. There is no 1 over 0. All right, and then I keep the same sign. Now, I know the absolute value function only stays in quadrants 1 and 2. That means the reciprocal also stays in quadrants 1 and 2. Okay, there's no graph down here or here. Ultimately, what I'm graphing is 1 over absolute value of x. Okay, this thing can never be negative. So 1 over absolute value, that still can never be negative. And then here's the game that I play. If I start at 1, 1, right? Here it goes up. Therefore, this will go down. Going backwards to the origin, this goes down. So this goes up. When one goes up, the other goes down. If the function increases, the reciprocal decreases. And do the same thing here. They touch at -1, 1. Then if we look at the original absolute value function, here it goes down, right? So if this goes down, this goes up. One increases, one decreases. And then over here, the black graph, that goes up, that increases, so this decreases. So I end up with the red graph, which I have right here.
So
You end up with an
the-
asymptote. An asymptote is a line that the graph approaches. So the y-axis turns out to be an asymptote for the graph. So the final answer is this and this. It's supposed to be red. I'm not sure if you can see the red, but it's supposed to be red.
So do the lines of the reciprocal graph are they always curved since they can't hit zero on either axis?
Are they always curves? They don't always have to be curves, but they're most often curves. Is probably the best way to say it. Okay, usually they're going to be curves. Okay. All right, so a quick summary. I got my original V shape. Okay, so undefined at x equals 0. You can't have 1 over 0. So there's no point here, no ordered pair. The functions match at 1 and -1. There is no -1 here. So here the y value is 1, here the y value is 1. What's the reciprocal of 1? 1. So they touch here. And then I just play the game of if one goes up, the other goes down. Okay? One must increase and one must decrease. So if I start at my y equals 1, right? The original graph, absolute value increases. This increases, so this must decrease. And approaches the x-axis as an asymptote. Okay? Now, if I take this point here and go back to the origin, this decreases. So if this decreases, this must increase. And just keep doing that over here. Okay, so they match at y equals 1. Whoops. They match at y equals 1. Then the original graph decreases. So if this decreases, this must increase. One increases, one decreases. Okay. And likewise here, this must increase, so this must decrease. And so I end up with that right over there. I'll do more. Many more. I'm going to end up doing almost all the problems, frankly, but that's okay. I'm sure you don't mind. Okay, back to number 9. I am going out of order, but I wanted to show you the absolute value first. Okay, g of x equals x minus 3. Number 9. All right. Linear. Slope is 1. Y-intercept is -3. So there we go. Slope is 1. Y-intercept is -3. Slope is 1 over 1, up 1, over 1, up 1, over 1, up 1, and so on. Okay. So this one, it's supposed to be green. I don't know if you can see it's green, but x minus 3. So how do I graph the reciprocal? 1 over x minus 3. Okay. So first I say, where is this equal to 0? 3. Which means for the reciprocal function, undefined. And you can tell that right here, right? If you put 3 minus 3, you get a 0 on the bottom, and that's a mathematical no-no. So x equals 3 becomes an asymptote. Okay, one more time. The graph looks like this. Where is y equal to 0? At 3, x-intercept. Which means for the reciprocal graph, there is no graph. You can't have 1 over 3 minus 3, 1 over 0. Doesn't make sense. Then I look for where is y equal to 1 and -1. Okay, y equals 1 here, looks like it's 4. Well, you can tell, right? What do you get when you plug in 4? 4 minus 3 is 1. And down here, y is -1. Looks like 2. What do you get when you plug in 2? 2 minus 3 is -1. Okay, so right here, the two graphs match. So again, strategy, where's the function equal to 0? The reciprocal will be undefined. Okay, so x equals 3. Okay, look at the original, say, oh yeah, x equals 3 makes it 0. Okay, so that means the reciprocal function is undefined. Okay, got an asymptote there. Then I look for 1 and -1. In this case, it happened at what, 4 and 2? And you can check, even here, what do you get when you plug in 4? 4 minus 3 is 1, 1 divided by 1 is 1. They match. And this was x equals 2. what do you get when you plug in 2? 2 minus 3, -1. 1 divided by -1 is still -1. Okay, so the first fundamental parts are the two graphs match here. How come? Because the y values are 1 and -1. We're doing reciprocal, right? So the reciprocal of 1 is 1. The reciprocal of -1 is -1. The reciprocal of 0 is undefined. And after that, I just simply play the game of one increases, the other decreases, right? If the function becomes large, the reciprocal becomes small, and vice versa. But the same sign. The reciprocal of a negative is negative. The reciprocal of a positive is positive. So if the graph is above the x-axis, the reciprocal is still above the x-axis. And if the graph is below the x-axis, the reciprocal is still below the x-axis. Okay. So match right here, the two graphs touch. Okay, now here, the original graph increases. So if this increases, this must decrease. Goes down as an asymptote. And then let's see, for this tiny part right here, if I'm going from a height of 1 back to the origin, so if I go from right to left, this decreases, right? So this decreases, this must increase. So it goes like that. And then over here, I look at where they touch. Let me look at this. Now I go back to the origin. So for the original graph, that straight line increases. So here, if the graph increases, this must decrease. And if I go here toward -infinity, right? So this decreases. So if this decreases, this increases up to the asymptote of the x-axis. Remember, it can't cross. They're always of the same sign. So negative, negative, positive, positive. So you say, how come it doesn't go up like that, right? It's because the reciprocal of a negative stays negative. So even though it's increasing, you can't get past the x-axis because otherwise it would become positive. Because the reciprocal of a negative is still negative, the reciprocal of a positive is still positive. Right? So that's what happens in this case. So my asymptotes are x equals 3 and y equals 0. The x-axis there. Okay, then a harder one is 13 x squared minus 1. But if you just faithfully use the rules that we always had, you should be okay with that. Okay, g of x squared minus 1. Okay, quick review. You should know what x squared looks like. Parabola, vertex of the origin. And then what's the effect of the minus 1? Just take that parabola and shove it down 1 unit. So this is my original graph, x squared minus 1. Now, the reciprocal is 1 over x squared minus 1. Okay, so I notice what happens when you plug in 0? -1. And what are the x-intercepts? If you put a 0 here, you can tell that plus or minus 1 make it true, right? If you plug in 1, you get 0. If you plug in -1, you get 0. So -1, 0, 1, 0. Here I got a height of 1. How did I get that? Well, if I set g of x equal to 1, right? I'll show you a little bit of algebra. 1 equals x squared minus 1. Come back into focus here. Add 1 to both sides. 2 equals x squared. So x is plus or minus the square root of 2. So what did you want to get that for? I wanted the heights of 1 and -1 because that means the graphs are going to match. Okay, so here's my original parabola. Vertex at 0, -1. Touches the x-axis at -1, 0, 1, 0. And when is y equal to 1? At negative radical 2, comma 1, and positive radical 2, comma 1. Notice if I plug in either a square root of 2 or a negative square root of 2, when you square it, you get 2, right? And 2 minus 1 is 1, right? So key points are here, here. How come? Because the y is 1. Here, because the y is -1, and here y is 0. All right, so now for the reciprocal function. Here, the original graph y is 0. Translation, undefined. You can't have 1 over 0. Right? And you can tell, right? If you plug in 1, what do you get? 1 minus 1 is 0. 1 divided by 0, can't do it. Likewise, -1. -1 squared, 1. 1 minus 1, I get a 0 in the bottom, can't do it. So asymptote, asymptote. Then I look at where the y value is 1 or -1. -1. They match. +1. They match. So undefined, undefined, you can't have the reciprocal of 0. Match, match. How come? The y values are 1, the reciprocal of 1 is 1. And match here because the y values are -1. And then I do the increasing, decreasing game. And keep in mind the same sign game also. So the reciprocal of a positive is positive, reciprocal of negative is a negative. So once the graph is positive, right, the reciprocal will stay positive. And once the graph is negative, the reciprocal stays negative. Okay, so I'm trying to look at the original parabola. Okay, so if I just kind of go piece by piece. Okay, so here, the original increases, therefore the reciprocal decreases. Increasing, decreasing. Now here, I come back down towards 0. So if I go from right to left, this decreases. So if this decreases, this must increase. And then right here, whoops. All right, the original parabola is below the x-axis. Negative. The reciprocal of negative is negative. So the new graph stays below the x-axis. Okay, they match here. And then if I go in this direction, the graph increases. So if this must increase, this must decrease. Same thing here. If I go from here back to 0, right? If I'm going in this direction, the graph increases. So if this increases, this must decrease. It looks like that. And same thing over here. I look at where they touch. So the original graph here decreases. So this decreases, this must increase. And finally, right here, the original graph decreases. So this decreases, this must increase. And there we go. So the actual final graph is that thing, and that thing. It's supposed to be in green. It looks more like colorful, I guess, if I'm looking at here, but I see, you know, when you project it over Zoom, the image may not come out as sharp. But if I'm looking at my own paper, this is meant to be green, green, green. I just picked a different color. That'll help me out a little bit more. Okay. All right, so that's that. A couple problems at the end. 21. Functions f and g defined by f of x is blah, blah, blah. G of x is x plus 2. How do the graphs of f and g differ? 21. Okay. So you may notice from algebra, you can factor the top into x plus 2, x minus 2. X minus 2's cancel out. So at first glance, you might think they're the same, but not quite, because this is the original function. X is not allowed to be 2 here. X is allowed to be 2 here. And in a certain sense, we're really saying, okay, back in your algebra 1, right? When you did this, and I did it too, I'm guilty of this as well. We actually were a little bit sloppy because we said, oh, factor, cancel, this is equal to this. Not quite, because here 2 is not allowed. Here 2 is allowed. Okay, so really truthfully, when you did this in algebra 1, right? And you said simplify, then factor x plus 2, x minus 2, cancel x minus 2, right? You really should say, but x is not equal to 2. But nobody feels like doing that, and for good reason. It'd just be too cumbersome to keep writing that down. Okay, so technically, these two are not the same. Only at one x value, 2, because 2 is allowed here, right? 2 plus 2 is 4, but 2 is not allowed here. You're never allowed to divide by 0. So the answer is they're different because f of 2 is not defined. If you look at the original function, which this is, right? 2 is not allowed, but g of 2 is defined. And I can illustrate that with a graph. Okay, what is the graph of this? Well, this looks exactly like this, except at x equals 2. So take the line y equals x plus 2, and it's like you punch a hole, right? Just punch a hole at 2, 4, and that's what the graph looks like. So it's a straight line, and there's a hole at 2, 4. So that's
Professor.
officially the graph of x squared minus 4 divided by x minus 2. Okay, because this is the function x equals 2 is not allowed here, but x equals 2 is allowed over here.
Professor.
Okay. Yeah,
Is
question?
is the whole function undefined, even if it's only one point that makes it undefined?
Is the whole function undefined? No, the function defined everywhere except that 2.
Okay.
So if you ask for the domain is all real numbers except for 2.
Okay. So if a question like that came up on a quiz, could we write that f of x is defined except at
Yeah, so on a
okay.
quiz or exam, just put this exact language.
Okay.
Okay, so f of 2 is not defined, but g of 2 is defined. So they don't quite have the same domain. So the graph of this plugs up the hole. The graph of this, it's like you have the line and I just puncture a hole there, just punch it, puncture the tire, so to speak, right there, but the rest stays intact. Okay, and finally 17 and 19, you're asked to look at the graph. I think the easiest way to do this is just to make a quick table. The graphs of f and g are given. Sketch the graphs of f plus g and f minus g. Okay, so for 17, it looks like the graph is going down. So I just make it a table. It went -2, -1, 0, 1, 2, 3. It looks like it at -2. Well, let's do this. 0 gives me 2, right? So for 17, let's say 0 gives me 2. I'm looking at g. -1 gives me 3. -2 gives me, I'm going to assume that's 4. And then 1, 2, 3. 1, 1, 2, 0, 3, -1. It just goes down in a linear fashion, right? I'm just reading off the graph. For the g function, -2, 4, -3, 1, 0, 2, 1, 1, 2, 0, 3, 1. At 3, -1. I do the same thing for f. A little bit harder. So f, the red function, 0, 0, right? And let me try to avoid the fractions for now. Looks like 2, 1. And -2, -1. It's linear, so I'll just go what, -0.5, +0.5, 1.5. Right, just reading right off the graph. For the red graph, -2, -1, 0, 0, 2, 1. Those are nice ones. And then I just went in between. Okay, then I just add f plus 3. So that plus that is 3. That plus that is 2.5. That plus that is 2, 1.5, 1, and 0.5. F minus G, subtract. That minus that is -5. That minus that is -3.5. That minus that is -2. That minus that is -0.5. 1 minus 0 is 1. 1.5 minus a minus 1, 2.5. Okay, and you just graph it. It looks like I have to go out to 5 is my biggest number. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. 2, 3, 4, 5. I want to go out of focus on this every now and then. There you go. Okay, so F plus G. -2 gives me 3. 1, 2, 3. I'll avoid the fractions. 0 gives me 2. 2 gives me 1. And the halfways will join as necessary. So I'll just connect the dots here. F plus G. And then F minus G, same thing. -2 goes down to -1, 2, 3, 4, 5. That's down here. And I'll skip the fractions. They'll show up if done correctly. 0 is -2. That's over there. 2, 1. And that should be good enough. The fractions will show up. And there's F plus G. And that takes care of that. All right, folks, I'm officially done with 2.3. I'll get started with some of 2.4, and we'll continue with that on tomorrow. Okay, so let me put this away. So 2.4 is in a much more difficult topic of composition of functions. Okay, a function of a function, f of g of x, for instance. Okay. Composition of functions, page 102. Okay. F of g of x, it looks like fog almost. F circle g of x means f of g of x. It's a function of a function. Okay? And order of operations, you do the inside first. So if you ever see something like this, right, you do the inside, that means you do g of x first, get that answer, and then after that, you apply f. Okay, so fog, f circle g of x, means f of g of x. Okay, and I'll show you how to do stuff with that. Let me check the chat quickly. Is our quiz on 2.2 and 2.3? It could be, it should also be some of 2.4 also. Okay, I'm going to give you enough that I think you should be able to do some of 2.4. So composition of functions. And so 2.4, again, ignore any dates. Composition of functions is a function of a function. So f circle g of x, that's the way we say it. F circle g of x, it looks like fog. It's f of g of x, like that. And by the way, you can reverse it. Looks like golf. G circle f of x means g of f of x. You're allowed to compose f with itself. So f circle f means f of x. and etc. You could have G circle G, G of x. Can I just mention quickly, composition of functions in general is not commutative. That means f of g of x is not necessarily the same as g of f of x. Sometimes it might be, but quite often it's not. And we can see that right away if I show you some examples. So it's a function of a function. Composition of functions. Okay, so let me show you the problems for those of you who don't have the book and aren't getting it. 1 to 23 odd, page 109. There you go. Sometimes this camera goes out of focus on me for no reason. That should be that. Let me see what else. Yeah, that's it for that page. Okay, yeah. So find fog, F circle G, but just for fun, I'm going to do G circle F. It's extra practice, and then you'll see what happens. Okay, so the original f of x is 2x minus 3, g of x is x squared plus 2. What is f circle g of 3? It means f of g of 3. Right now, by order of operations, you do the inside first. So only look at g of 3. Sometimes I cover things up. You say, oh, there's too much stuff. I get confused. Right? Don't even look at the whole thing, right? Just look and say, okay, by order of operations, I do what's behind my pen first, right? You go inside out. So I focus only on G of 3. Okay? Suppose all you saw was that, G of 3. So, okay, I can do G of 3. That means plug in 3 right here, right? So what do you get when you plug in 3? 3 squared is 9, 9 plus 2 is 11. Okay, so that's 11. So now I put that as 11. Okay, if I only look at that, I'm supposed to do that first anyway, right? G of 3, that's 11. 3 squared is 9, 9 plus 2 is 11. So that's 11. Now I'm doing f of 11. This thing here was my G of 3, came out to be 11. So now I take that 11 and apply it to f. Right? 22 times, 2 times 11 is 22. 22 minus 3 is 19. So the final answer is just 19. Now, suppose I switch it. G circle f, G of f of 3. So G of f of 3. So by order of operations, again, my suggestion, if it looks too complicated, there's too much stuff going on, or there's too many parentheses, I don't get it. But just think of what I'm supposed to do first. Just cover it up. I see f of 3, right? I got to do f of 3 first anyway. So, oh, can I do f of 3? Sure. If all I saw was f of 3, that means you plug in 3 right there, right? So what do I get when I plug in 3? 2 times 3 is 6. 6 minus 3 is 3. Oh, I get back 3. So now I take that 3, put it back into G. Right, so that f of 3 thing came out to be 3. And now I'll take that 3 and plug it into the G function. Okay, so 3 squared is 9. 9 plus 2 is 11. And you may notice that they're not the same. So yes, indeed, in general, G circle F is not the same as F circle G. Okay, number 3, as for F of G of -3. F of G of -3. So oh, there's too much stuff. I get confused. Don't even look at the whole thing. Just say, what am I supposed to do first? G of -3. So, don't even look at this. Focus only on G of -3. And then I say to myself, can I do G of -3? Okay, that's not that bad. To the G function, plug in -3. -3 squared, 9. 9 plus 2 is 11. All right, so I say to myself, okay, so the next step, change this mess to 11. Right? That thing right there, g of negative 3, I've established as 11. So I now write it as f of 11. And then I say to myself, what do I do for f of 11? Well, sure, for the f function, not the g function, you plug in 11. So put 11 right there. Oh, didn't we just do that? 2 times 11 is 22. 22 minus 3 is 19. Okay, how do you do a function composed with itself? F of f, or g of g, or whatever, right? So 5, f circle f of negative 2. It means f of negative 2, right? And again, unless you say, oh, I'm dizzy, I don't like looking at all the f's. Don't look at the whole thing, maybe. This is what I like to do, just cover it up. Order of operations, I go innermost out, right? When you have parentheses inside parentheses, you do the innermost, and then you work your way back out. So I look at this and I say to myself, I got to do f of negative 2. So don't even look at the rest of the stuff. If all I saw was f of negative 2, can I do it? Oh yeah, sure. Just take the negative 2, plug it into the f thing, and worry about the rest later. Okay, so put negative 2 right here, right? So 2 times negative 2, negative 4. Negative 4 minus 3 is negative 7. All right, so I've established that this is negative 7. So now the stuff behind my pen, f of negative 2, I now know it's negative 7. Take that negative 7 and plug it back into the same function, f. So I say, okay, can I do f of negative 7? Well, sure. Just plug in negative 7 to the same function. So 2 times negative 7 is what? Negative 14. Negative 14 minus 3 is negative 17. Final answer is negative 17. Okay, I was just going to show you one more of this type. And yeah, I might give you something like this on the quiz tomorrow, but I'll do more examples. Keep this back in focus. Find f circle g, g circle f, and give the domain of each composition. Okay, what if they don't give me numbers, like 3 or negative 1 or whatever? All they do is give me functions. So function of a function. So here's f, here's g. So f of x is 2x plus 1, g of x is 3x minus 1. Okay, they want fog, f of g of x means this, f of g of x. You can say, oh, too confusing, too many parentheses. Okay, don't look at the whole thing. Order of operations, start with the innermost. Okay, so don't even look at this. Literally, either literally cover it up or just focus your attention on the inside. Don't look at the rest. G of x. What is g of x? Right there, 3x minus 1. So here's the next step, okay? That f, the left paren and the right paren don't change, correct? Order of operations. Leave alone the f, left paren, right paren, okay? Leave alone f, left paren, right paren. Inside supposed to be g of x. But I don't literally write g of x. I write down what it's equal to. F of 3x minus 1. And then, just like any other function, the game I play, let me cover these up. Whatever is behind my finger here goes right there. And maybe the best way to think of the function in general is this. Whatever is behind my pen on the left, I put the exact same thing on the right. Start easy. Suppose behind this pen, it's at f of 2. You would plug in 2 right there, wouldn't you? Suppose it says f of pi, you put pi. Suppose it said 1,000,000, you go 2,000,000 plus 1. If it says f of a mess, I don't care. 2 times that mess plus 1. Well, what is the mess? 3x minus 1. So guess what goes right over here? That mess, 3x minus 1. Right? This is my g of x. And then I just cleaned it up. So 6x minus 2 plus 1, 6x minus 1. Okay. I trust you can do that simple algebra there. If you were my algebra 1 class, I wouldn't go that fast. This one, I think you can see 6x minus 2 plus 1. Oh yeah, minus 2 plus 1 is minus 1. Okay, do the same thing with Goff. G circle f of x, which means g of f of x. Oh, too dizzy. I don't like looking at all that stuff. Don't look at all this stuff. Order of operations, I go inside f of x. So the first thing I'm going to do is I'm going to leave that g alone, that left paren alone, that right paren alone, and then inside is f of x, right? So right here, the next step, I do not write f of x, I write down what it's equal to x plus 1. And then this thing gets applied to g. 3 times blah, 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 minus 1. Okay, so again, let me cover the pens up. This is what g does. Multiplies it by 3 and subtract 1. Suppose it's g of 7. You would go 3 times 7 minus 1. Suppose it said g of 1,000,000. 3 times 1,000,000 minus 1. Suppose it says g of w. 3w minus 1. Suppose it's g of something complicated. 3 times something complicated minus 1. I do have something complicated. There it is. 3 times that complicated thing minus 1. And then clean that up. 6x plus 3 minus 1, 6x plus 2. And again, notice they're not equal in this case. So f of g and g of f don't necessarily have to be the same. They might, but it looks like they're not in general. And the domain is all real numbers for both graphs. These are both linear. You can put anything in here. You can put anything in here. You can put anything in here and here. So the domain is all reals for both of them. Okay, but next time I'll do more complicated examples of fog and Goff. Okay, so you have to be ready for this fog and Goff stuff potentially for the quiz tomorrow too. But you know, it's open everything. You can look it up. You can talk about it, and it's not due until 11:59 p.m. tomorrow. So you have the rest of the day to finish the quiz. Okay. All right, so we're just about out of time. See any quick questions? It's 9:58 and we're almost out of that time anyway. So something quick, please. Otherwise, that's it. All right, that's it for today, folks. So everybody have a good day and we'll see you next time. Okay, bye, everybody.
Thank
Thank
you.
you.